Okay, so methodology. So this particular research work is actually part computational as well as part experimental. So in order to proceed with the simulation part, we have to deal with the modeling as well as physics definition and beam generation. On the experimental side, we have material setup, then there's parameterization as well as beam measurement. Now, both of which will undergo initial simulation and initial experimentation. The dose generated by both shall be evaluated initially, and then once if they are in agreement, we shall proceed with phantom remodeling as well as phantom replacement, and then of course for our final simulation as well as final experimentation. Now again, the dose generated by both shall be evaluated as a sort of final evaluation. Okay, so talking about phantom design. So anthropomorphic phantoms are actually used as patient substitutes because number one, they are of good tissue equivalence. And then second is that they are actually closest to clinical human anatomy. Now, besides anthropomorphic phantoms, we also have the PMMA's love phantom as well as the PTW water phantom. Now, so far, we had been introduced to the CIRS Phantom. There's another Phantom available in the market, which is Random Phantom, but for the purposes of this particular research, we shall be using the CIRS Phantom as the model phantom for the 3D printing of our breast phantom model. Okay, so a choice between ABS and PLA plastic is what is commonly used in the 3D printing industry. A comprehensive study has been conducted previously by J.P. Bustillo et al. In 2015 regarding the two material, basing on their relative mean electron densities as well as their corresponding mass densities. So take note that for 100% ABS, the relative electron density is 0.915, while the mass density is 0.926. PLA, on the other hand, has an electron density of 0.988 and a mass density of 0.99. So ideally, we are actually looking for a density which is closest to unity because it represents the soft tissue or the organ itself. So therefore, our 100% infill PLA should represent solid water and therefore our soft tissue or the body itself, while the lung actually is represented by a 20% infill. We are referring to 20% PLA and 80% air. Three-dimensional or 3D printing, otherwise known as additive manufacturing, is a process of creating three-dimensional solid objects using a digital file. So, as previously mentioned, the 3D printing of the material shall be primarily carried out by 3D2Go Philippines. Right, so in order to do such, a 3D model is needed. Here is an example flowchart in creating an STL file. So first, there's scanning of the CIRS Phantom. Then there's importation of DICOM files to the 3D Slicer software. In the software, there shall be volume rendering. Once the volume has been rendered, it should be segmented, and then right after, it shall be smoothed and triangulated. So the final output will be in stereolithography file or STL file. So here is an example of the 3D volume rendering for the body. Then we have the lung. Then we have the spine component. Here we have on figure A the SL file generated using the 3D Slicer program. Figure B is the polygonal meshing of the lung, also an STL file with 0.5 decimation applied. Then lastly is figure C, which is the actual pattern used in cutting the phantom. So there you go. So here is the final output of the 3D modeling. Alright, so now let's talk about Monte Carlo. Monte Carlo methods or Monte Carlo experiments are a broad class of computer algorithms which relies heavily on repeated random sampling just to obtain numerical results. Now, for our case, the MC technique consists of a computer program which simulates a transport of millions or even billions of photons in particles through matter. Now, they say the larger the number of simulated particles or number of events, the greater is the accuracy of predicting their distribution. Generally, there are several multi-purpose Monte Carlo systems for those calculations. So among those are electrogamma shower or EGS. We also have Monte Carlo N particle or MCNP, as well as penetration and energy loss of positrons and electrons or Penelope. Also, we have Gatsby Core, and lastly, we have a free software package written in C++, which is the GN4 and tracking. Now, Gate actually is a daughter application or a sub-application of GN4. Also, there's another newer breed of application, which is the Prima Monte Carlo software, which is still being reviewed and studied as of the moment. Okay, so system requirement. This particular simulation is in need of a 2.8 gigahertz processor or better in a Linux Ubuntu operating system. Now, alongside the Gate software package, three other known dependencies needs to be downloaded as well. So we have number one, which is the root plotting system, which is needed for post-processing and of course plotting. And we also have the HempRep browser as well as the Qt browser for the external and the internal visualization respectively. Okay, so now how the simulation. Right, so to set up the gate simulation system, the following requirements are needed. So we have volume geometry. It's further divided by the scanner geometry and then the phantom geometry, which is our water phantom and our 3D printed material. Next is the physics modeling. Also, we have source definition as well as random number generation and scoring plane detection. Now, as mentioned, it's using a 2.8 gigahertz on a Linux Ubuntu system. The gate version applied is version 8, open source coding. And the software we have is a mid-Linux package. And then we have the HEPRAP external visualizer and then Qt internal visualizer. And so as per geometry definition, we have here a blue box, which is represented by the universal or the mother volume. Inside the box, we have three other daughter volumes, namely daughter volume number one, which is the Linux Gantry head. The second volume is the water phantom, and the third one is the breast phantom model. Okay, so here you'll see a schematic diagram of a typical linear accelerator. Now, since we are only after the production of X-ray or photons, we shall be focusing on the components of the Linux Gantry head, hence the red circle. Now it shall serve as our basis for the geometry construction. Less MLC. Incident to the beam, we now have the target. Then we have the primary collimator. Then flattening filter as well as a monitoring ion chamber. Then the mylar mirror. And lastly, the upper and lower jaws. Right, so here is an example of a 3D visualization of the previously mentioned components of the Linux Country head. We actually based our geometry construction on the manufacturer specification of a 6 MB Electa Compact linear accelerator machine. Right, so for this particular study, we actually made use of a two-way setup. So in the first setup, a water phantom is used. Now, once it's validated, it shall then be replaced with the 3D printed or the 3D fabricated phantom. Now, of course, following the same parameterization, number one is that it should be of a 6 MB photon energy Linux machine. Second is that SSD should be at 100. Third is that field size is set to 10 by 10. And lastly, with a depth of 10 as Tmax. Alright, so here's a sample coding of the Gate Monte Carlo simulation. Now say we pick one file, namely main.mac. This particular file actually contains a majority of the coding intended for the simulation. Now here's one executory line. Now in order to set the world volume, we follow the following command lines. Right now for the water phantom, we named it here as the water box. So we also follow this particular command line here. Right, so the following command lines are actually on a basic template already. You just have to replace the necessary details which is specific to the machine, right? So here is an example 3D visualization of the world volume and the water volume as well as the Linux country head. So we have codes actually set for various volumes and shapes as well. So most of which can be found at the user's guide manual. Right, so now let's go back to our 3D visualization. Here you'll see that the blue box is actually represented by the water phantom. Now the remaining upper cluster is represented by the components of the Linux country head, hence the yellow circle. Now if we're going to magnify that, you'll see here is the target, then flattening filter, as well as the parallel ionization chamber, then of course the mylar mirror, and then the upper and then the lower jaws. Right, so here is an example of a beam generation. In order to begin the simulation, we have to make use of the following command lines, circled in green. Now we just have to replace the number by the numbers specific to your laptop or to your desktop. Now for our case, our maximum capacity is around 2 billion events, hence this particular line. Right, so despite the limitation, you actually have the option to do certain repetitions until such time that the accuracy and precision is achieved. Right, so FYI, a normal simulation run usually takes about days to weeks. Now it depends on the laptop specification as well as the total number of events. Now for our case, since we're using 2 billion events, it actually took us 2 to 3 days to complete the whole simulation process. Right, so for the decoration of the chemistry of the materials, we actually made use of the ones available online. So for PLA, there's this specific material safety data sheet, which states that the molecular formula for such is 66H8O4. Same is true for the dimethyl silicon fluid, though the molecular naming is provided by Polytech. Molecular formula is C11H30O3 silicon 4. And lastly, we have the magnetic disk, which is actually a neodymium material, which has a nominal density of 7.4 grams per cubic centimeters. Right, so moving to experimentation, we are actually in need of a linear accelerator machine or a LINAC. Also, we are in need of a medical physics software or the Midfisto tool, as well as a PTW water tank scanning system, and then of course the ionization chamber as well as the tandem equipment. Alright, so here is the ideal experimental setup. So on this side, you will have the 6MB Linux machine, and then right below it is the dual channel electrometer or the tandem equipment. And on top of the water phantom, we have the relative and field detectors, which is actually thimble type ionization chambers. And of course, our PTW water scanning system, which is right below the Linux Gantry head. And lastly, the Midfisto software for the post-processing and analysis of beam measurements. Right, so in order to proceed with beam validation, we have to perform the following step-by-step procedure. Number one is that we have to set the Linux country and collimator angles to 0 degrees. Second is that we have to align the center of the water phantom along the beam central axis. Third is that we have to align the level of water to spirit level using the bubble meter. Fourth is that we have to set the source to skin distance or SSD to 100. Also, we have to connect the field detector for the photon beam to the water scanning system. And then also we have to move the detector along X, Y, and Z to ensure that it is passing through the beam central axis during the scanning process. And so number 7, we then have to place the reference detector on air at the border without having to interfere with the detector's path. Right, so number 8 is that we have to search the depth of maximum dose in the central axis while the beam is on, and then scan the central axis with the normalization of the maximum dose for a 10 by 10 field size. All right, so we then have to scan the beam profile at a depth of 10 cm. Lastly, we are to compare the normalized error of the Monte Carlo beam data with that of the experimental result. Right, so as earlier mentioned, once the beam data has been validated, we then proceed with the phantom replacement, and hence we are to satisfy the 4 different satisfying conditions, namely number 1, to have a breast with a silicone gel implant. Second is to have it filled with saline solution. Third is to have the saline solution plus the magnetic valve. And lastly, to irrigate a full intact breast. Basically, we're done with beam validation. Now we are to proceed with the actual experimentation and the final simulation, both of which are actually a work in progress.